Okay, so we will continue with chapter 20. Last time we talked about Claisen condensation. So we had an enolate of an ester, and that enolate was attacking another mole. And we talked about this reaction in details. Like aldol condensations, we were able to do a mixed aldol condensation. We can do a mixed Claisen condensation. In this case, you need to use an ester that cannot generate an enolate. It's similar to the case of mixed aldol condensation. So these esters do not have any alpha hydrogens and therefore cannot generate enolate. So these esters are ideal for mixed Claisen condensation. For instance, if we take the methyl benzoate and we reacted with the methyl propanoate in the presence of sodium methoxide first and then H3O+, we can achieve the mixed Claisen condensation product. So you have the enolate of this ester to attack. You're getting O-. O- will come back, will kick out OCH3. Then you have an acid-base reaction. All of these, they will happen upon condition number 1. Then you add H3O+, that will get you the final product. So the C- will be protonate. Another example, if you take cycloheptanone and you reacted with diethyl carbonate, what you, in the presence first of sodium hydride and then H3O+, you can actually achieve the acylation of a ketone. So with the sodium hydride, you're generating the enolate, and then this enolate is attacking. You're getting O-. O- will come back, will kick out the methoxy, the ethoxy. You have an acid-base reaction. That will be upon condition number 1. Then you add H3O+, so you will protonate the C- right here. So the end result of this, you have added the C double bond OOCH2 CH3 at the alpha carbon to a ketone. Another example, if you take acetophenone with the ethyl benzoate, you can get the mixed Claisen condensation product, and in a very respectful yield, in 62 to 71% yield. Now, what about taking this alpha beta gamma keto ester, and you reacted with the sodium methoxide and H3O+. In this case, you have these alpha hydrogens that are acidic, you have these alpha hydrogens that are acidic, and you have these alpha hydrogens that are acidic. If you make the enolate at this carbon and you attack this carbon, then you will get 1, 2, 3 member ring. If you make the enolate at this carbon and you attack this carbonyl, you are going to have 1, 2, 3 member ring. However, if you make the enolate at this carbon and you attack this carbonyl, now you have 1, 2, 3, 4, 5 member ring. So this enolate is attacking the carbon. You're getting O-. O- will come back, will kick out the OCH2 CH3. And then you will have an acid-base reaction so that you are getting C-. And then you add H3O+, the C- will be protonated. With that in mind, let's sum up all of these by going over this question. What is the product of the following reaction? Okay, I'm going to close the poll. 31% answered 1, 19% answered 3, and 50% answered 4. The correct answer is 4. So let's go over the mechanism of this reaction. You have the enolate to be formed first. So the sodium ethoxide, again, the direction of the equilibrium is towards the starting material. You are going to form the enolate. We have an intramolecular Claisen condensation. We number the carbons to guide us to know about the connections. So we are forming a 5-member ring. This is carbon number 1 attached to 2, to 3, to 4, to 5. At carbon number 1, you have an O minus and an O ethyl. At carbon number 5, you have a C double bond O, O ethyl. Then the O minus will come back, will kick out the ethoxy group. The direction of equilibrium is still to the starting material, and you will get this beta keto ester. Now, an acid-base reaction will drive the equilibrium towards the enolate of the ester, of the beta keto ester. So this ethoxy is going to pick up the alpha hydrogen, and you will form this enolate. All of this is condition number 1. Now, condition number 2, you're adding H3O plus so that will get you the Claisen product. Then we are adding sodium hydroxide. So we are performing what? Saponification. So this is condition number 3. You're forming the carboxylate. Now you are adding D3 O plus and heat. I'm going to do it in steps. So with D3 O plus, you're forming C double bond O, OD. And with heat, you are going to get rid of this CO2 group. And what you are going to form is the 2-deuteriocyclopentanone. The correct answer is 4. Any questions? Yes?
In the second step, we added D3O plus, we would have 2 deuterium.
That's right. Very good. So if at the second step we did not add H3O plus, but rather D3O plus, then you are going to get a deuterium over here. And then by doing another, by adding sodium hydroxide, which is saponification, and then adding D3O plus, so that you will get the O minus to be deuterated, and then with heat, that means you will get 2,2-dideuteriocyclopentanone. Any other questions? Okay, we'll carry on. Now, we're going to talk about alkylation of enolates. So when you form an enolate of a beta keto ester, you can actually use that enolate as a nucleophile, you can perform an SN2 reaction if your alkyl halide is primary or secondary. If your alkyl halide is tertiary, the elimination product is going to be the major product. So the enolates that are derived from beta diketones as well as from beta keto esters can be used as nucleophiles in SN2 reactions. For instance, if you have this beta diketone and you reacted with iodomethane in the presence of potassium carbonate, you can get the alpha carbon to be methylated. What you form is an enolate in the presence of a hydroxide ion. That enolate is attacking the carbon in an SN2 reaction, and the iodine is leaving. You can also have an SN2 reaction by forming the kinetic enolate of 2-methyl cyclohexanone, and then reacted with the benzyl bromide, for instance. So you are adding LDA, so you're getting the kinetic enolate. The kinetic enolate is attacking the carbon, bromine is leaving, and that is going to be your major product, 52%. You have 7% coming from the thermodynamic enolate. Any questions? Okay. Well, lithium diisopropylamide can also generate the enolate of an ester quantitatively. So if you have this enolate and then you reacted with an iodoethane, you can get the alpha carbon to be reacting in an SN2 reaction, and you are adding an ethyl group. Now, previously, in a previous lecture, we covered the synthesis of the ethyl acetoacetate or the acetoacetic ester synthesis. And now we are going to take that ethyl acetoacetate and we're going to form an enolate out of it. And we are going to do an SN2 reaction. And then we are going to get rid of this group and we will be forming a ketone. So we are going to use the enolate of the ethyl acetoester to synthesize a ketone. And we are going to talk about that towards the end of this lecture about what's called a synton. A synton is a synthetically equivalent material to something else. So, and that is going to be very important when you are designing synthesis using enolate chemistry. So these two hydrogens are acidic. The pKa values of these hydrogens is in the order of 11. You can generate the enolate. That enolate is stabilized by resonance. The direction of equilibrium is towards the enolate because you're going from pKa 11 of the ethyl acetoacetate to pKa 16 of ethanol when you are using an ethoxide ion. So you can take that enolate and you can do an SN2 reaction when your alkyl halide is primary or secondary. So once you are having this carbon to be alkylated, in fact, you can do another SN2 reaction. You can form another enolate and you can add another R or R prime. Then you can do saponification and then you can protonate it and then you can get rid of the CO2. That will lead to the synthesis of a ketone. So if you are taking that beta keto ester and you are doing the saponification and then heat, well, first H plus, you are going to get the beta keto acid, and heating it up will get rid of the CO2 group, and now you have synthesized a ketone. This means if you want to synthesize a ketone, you want to have an R1C double bond O CH2 R2. You are actually looking for a synthetic equivalent of R1 C double bond O CH2 minus. We will call this a synton. Because if you have this CH2 minus and you are having an R2X, you can do an SN2 reaction and this leave. Now, what is the synthetic equivalent of R1 C double bond O CH2 minus? The synthetic equivalent of R1 C double bond O CH2 minus is R1 C double bond O CH2 C double bond O OR3. Why? Because if you take that, you can make the enolate, you can do an SN2 reaction, then you can do saponification, and then you can protonate and then get rid of the CO2. So the synthetic equivalent to this synton is this beta-keto ester. And we're going to practice that. So let's go over more examples. If you have the ethyl acetoacetate and you reacted with the sodium ethoxide and then with the bromobutane, you can add at the alpha carbon the butyl group. Then if you take this and you do the saponification first, then you add H+, then you heat it, you will get rid of CO2. Now you have synthesized 1, 2, 3, 4, 5, 6, 7, 2 heptanol. Another example. Well, if you have this beta-keto ester and you are reacting first with sodium ethoxide and then with iodoethane, you can substitute the alpha carbon with the ethyl group, and that will be your product. Then you can take that product and you can do the saponification, then you add H+, then you heat it, you get rid of CO2, now you have synthesized this ketone. So this is going to be very useful in designing the synthesis of some complicated ketones by using this synton, the synthetic equivalent of the beta-keto ester. This is like an enolate. If you have CH3, the enolate of acetone. In fact, the ethyl acetoacetate is the synthetic equivalent of the enolate of acetone, because you have CH3, C double bond O, CH2 minus. If you have this beta-keto ester and you react with sodium ethoxide and with an allylic bromide, you can substitute the alpha carbon with the allylic group. So you don't need to use ethyl acetoacetate. As long as you have a beta-keto ester, you can use that beta-keto ester as a synthetic equivalent to the enolate of a ketone. Another example, well, actually, we're following up on this example. If you take this and you do the hydrolysis under basic conditions, so you're doing saponification, then you add H+, then heat, you get rid of the CO2 group, and now you have synthesized this ketone. Do you have any questions? Yes?
Isn't the tertiary enolate too bulky?
It will still attack in NS2. There is no problem. The only limitation for this reaction is that your alkyl halide must be primary or secondary. But there is no problem. As you can see here in the previous example, well, right here, actually, you had an anion right here. This anion is still attacking an NS2 reaction. But notice that this carbon is primer. Okay? Okay. Now, we're going to talk about another synthetic equivalent. And that will be achieved using the Malonic Ester synthesis. This is called the Diethyl Malonate. It's called also the Malonic Ester. This is going to be the equivalent, the synthetic equivalent of the enolate of a carboxylic acid. So if you are having the diethyl malonate, C double bond O, CH2, C double bond O, O, ethyl, this is the synthetic equivalent of enolate of acetic acid. Because you can take that enolate, you can do an SN2 reaction, and then you can do the saponification on both sides. Then you will protonate both sides, and then you can get rid of one CO2. Which means now you can synthesize carboxylic acids by using the diethyl malonate. In fact, the enolate of diethyl malonate. Let's go over this, and we will go over some examples as well. So what we are achieving now with if you are having an alkyl halide, using the acetoacetic ester synthesis, you will be able to synthesize a ketone. Using the malonic ester synthesis, you will be able to synthesize this carboxylic acid. How so? Well, this is diethyl malonate. Reacted first with sodium ethoxide, and then you are going to get a substitution at the alpha carbon. Now, you take this product and you perform saponification, then you will protonate it to the carboxylic acid, and then you heat it up, you will get rid of CO2. So what you are achieving upon conditions number 1 and 2 is simply the CO2H right here, and the CO2H right here. Then one carbonyl is going to assist the second carbonyl so that you will lose the CO2. What you are achieving upon conditions number 1 and 2 is this dicarboxylic acid. And then, upon heating it up, you're getting rid of one CO2, and the final product will be the indicated carboxylic acid. Do you have any questions? Okay, let's go over this question. What is the major product of the following reaction? Okay, I'm going to close the poll. 3% answered 1, 10% answered 2, 83% answered 3, 3% answered 4. Correct answer is 3. Again, let's go over the mechanism of this reaction. With the sodium ethoxide, you are going to generate the enolate of the diethyl malonate. So you are forming the enolate of diethyl malonate. Then you're reacting it with the tosylate. This is a very good leaving group. You have an SN2 reaction. This is a secondary. So this is going to attack this carbon. This is going to attack this carbon, and the tosylate is going to leave, and you are going to form CH, C double bond O, O ethyl, C double bond O, O, ethyl. Now, with the sodium hydroxide, you are going to get saponification product, so you are going to get the dicarboxylate. And then, with the addition of H3O+, you're going to get the dicarboxylic acid. And then with heat, you will get rid of CO2 group, and you will form this carboxylic acid. Do you have any questions? So if your alkyl halide is secondary or primary, you can do the SN2 reaction. If your alkyl halide is tertiary, you will get the elimination product. You can achieve dialkylation. So if you have diethyl malonate and you are reacting it with sodium ethoxide and then with bromomethane, you can put the methyl group, you can substitute the alpha carbon with a methyl group. Then you can do another alkylation by adding first sodium ethoxide and then one bromodecane. So you can get the dialkylation product. Now you can take that product and you can do the saponification. Then you can form the carboxylic acid, and then you heat it up and you get rid of the carbon dioxide. And that will be your carboxylic acid. Now, what about taking diethyl malonate and reacted with dibromopropane? So you're reacting first with sodium ethoxide and then with dibromopropane. You're doing the first SN2 reaction, but then you can take that product and react it again with sodium ethoxide, and now you are going to have an intramolecular SN2 reaction, and you can take that product, you react it with sodium hydroxide, then H+, and then heat, you get rid of the CO2, and now you have formed a cyclic system, and you have a carboxylic acid. So this is a concept of synton. So let's say you want to synthesize this carboxylic acid. So what you are looking for is a synthetic equivalent of CH2 minus C double bond O OH. What is the synthetic equivalent of CH2 minus C double bond O OH? The answer is diethyl malonate. So the CH2 minus C double bond OOH, we still have the drawings on this board. This diethyl malonate is synthetically equivalent to the enolate of acetic acid. Because you can take that diethyl malonate, you can make the enolate out of it, you can attack an SN2 reaction, then you can do the saponification, you protonate your dicarboxylic acid, you heat it up, you get rid of CO2. The same. The ethyl acetoacetate, if I have right here CH3, CH2, CH3, is synthetically equivalent to the enolate of acetone when you are doing a synthesis of a ketone. So you can use now the diethyl malonate to synthesize the carboxylic acid, and you can use the ethyl acetoacetate to synthesize a ketone. So for instance, if we are trying to synthesize a 3-methyl pentanoic acid out as, this is an exercise from your book, show how you could prepare each of the following carboxylic acids from diethyl malonate and any necessary organic or inorganic reagents. So you need the synthetic equivalent to CH2 minus C double bond OOH, and then you can have the required alkyl halide. The synthetic equivalent to CH2 minus C double bond OOH is diethyl malonate. You can do an SN2 reaction, and then you can do the saponification, then you can protonate, and then you can heat, and that will get you the 3-methyl pentanoic acid. Do you have any questions? Yes?
Sir, if we're supposed we don't have diester, for example, dipropyl, can it also work if we at the end of the day we are going to do the saponification?
Right.
Get rid of the
There is no problem with that.
So why is it
So if you are having a propyl right here, that's fine. Make sure you use the propoxide so that you do not have what we call trans-esterification. Okay? You make sure that the alkoxide that you are using is the same as the group that you have in the ester group. There's no problem with that. If it is not the same, you can have a nucleophilic attack from the alkoxide to the carbon, and then you are having another ester. Okay? So you avoid trans-esterification. Trans-esterification, it means you go from one ester to another ester. Okay, now we're going to cover something very interesting, and that is the alkylation of chiral enolates. And we're going to define the chiral auxiliaries. Basically, what you have is an enantiomerically pure chiral compound that you are able to attach to a substrate so that you can synthesize one enantiomer versus the other enantiomer. So you will make one of the two possible prochiral reactions a favorable pathway. And then you can remove that auxiliary axis and you will have a stereoselective reaction. So you are using what's called a chiral auxiliary. The chiral auxiliaries, they have been developed to control the direction of alkylation at the alpha carb. And I'm going to give you an example. It's from your book. One of the chiral auxiliaries that is used is a derivative of 2-oxazolidinone. This is 2-oxazolidinone, and that is the derivative of it. It is 4R5S, 4-methyl-5-phenyl 2-oxazolidinone. It is a chiral auxiliary. So what you have, you can take that chiral auxiliary and you react it with the propanol chloride, and what you are doing is an amide formation. So you are attacking the carbon, O minus will come back, will kick out the chlorine. So you are getting the N-acyl derivative. But then when you are adding LDA in THF, tetrahydrofuran, you will be able to form the enolate of this ketone, but the structure of the enolate is going to be as such. Why? The lithium is going to complex with these two oxygens. So you have the O minus right here, Li plus, and you are having also Lewis acid, Lewis base between the oxygen and the lithium. So you are having this lithium enolate. The fact that you are having this lithium enolate, you are going to direct the SN2 reaction, as you will see on the second slide. But what will happen? You are going to have an SN2 reaction. The enolate, the O minus will come back, and this double bond is going to attack this carbon, and bromine is going to leave, and you will get this one as a major product. In fact, 98% you are getting this product. Now, why are you observing the reaction so that you are going to get this CH3 to be towards you, this enantiomer versus the other enantiomer? Well, it has to do with the approach to the substrate. One face is less sterically hindered than the other face. So what you are having right here, this is more crowded. So if you are having this double bond to attack from here, you have a more crowded approach. But if you are having the double bond, because the O minus will come back here, you will get the double bond to attack this direction, it is less crowded. That is the reason why you are getting one enantiomer over the other enantiomer. And then what you can do, you can recover your chiral auxiliary by just having a hydrolysis reaction. You're back to the chiral auxiliary, and here you have synthesized an enantiomer of 2-methyl-4-pentanoic acid, so you're getting only one enantiomer. So the use of this auxiliary, the chiral auxiliary, has led to the synthesis of one enantiomer rather than having a racemic mixture or a mixture of enantiomers. So the end result, this is an example of what's called an asymmetric synthesis, and you can get a stereoselective introduction of a chirality center. There are many more examples of such approach, but we will not cover them in this course. I just wanted to share with you one example as it is actually listed in your book. So it is the presence of that lithium enolate that has favored one attack versus the other attack, and you are getting one enantiomer over the other enantiomer.